Aloha and welcome to another episode in the Women in Space Exploration Talk Series put on by Pisces. We're so excited to have you here with us today. My name is Mimi Fuchs. I'm a space enthusiast. I feel really lucky to have worked on the Mauna Kea telescopes for the last 5 years, and now I'm back in school studying to be an engineer. And today we are all going to be hearing from a really wonderful engineer working in space exploration. We are going to be hearing from Sara Langberg. Sara Langberg is an aeromechanical engineer at AeroVironment, and she's one of the lead designers on the Ingenuity Mars helicopter project. So you might have heard how at the end of this summer, at the end of July, we launched the Mars 2020 Perseverance Rover. And it's included with a really awesome buddy, a really cool helicopter assistance unit that we're going to hear all about from Sara. Before we get started, just a huge congratulations to the most recent Nobel Prize winners. We have 3 women who were honored with the Nobel Prize this week, 2 in chemistry for their work contributing to the CRISPR gene editing tool, Jennifer Doudna and Emmanuelle Charpentier, and for physics, and Dr. Andrea Gaze was honored for her contributions to black holes. She has worked so much with the telescopes in Mauna Kea, so it feels particularly exciting that she and these other women were honored. So, for some of us who haven't joined us before, the way that this speaker series works is we're going to give Sara about 30 minutes to give a presentation, and so we can learn about her career path and some of the work that she's been able to do, especially with this really awesome Mars helicopter. But stick around afterwards. We're going to have a 30-minute question and answer session. This is your time to ask all of your burning questions about what it's like trying to explore the Martian surface. How do you become an aeronautical engineer? And to ask anything you really want, anything at all. So the way that we're going to do that is by using our meeting chat window. So whether it's at the end of our presentation, whether something strikes you in the middle, go ahead, jot it down in the chat, send it along to us. Now, with the WiSE Talk series, we really want to help encourage those younger participants who are starting out in their careers. So if you're a younger learner, if you're just getting started in your career and you have a burning question for Sara, please include the hashtag WiSE in your questions. And so without further ado, I'm going to pass it off to Sara Langberg. Thank you, Sara.
Buddy. Thank you, Mimi, for that great introduction. As she said, my name is Sara Langberg, and I'm an aeromechanical engineer at AeroVironment. And I'm really excited to talk to you about a really special program that I was a part of, and that is the Ingenuity Mars helicopter. So Ingenuity is a technology demonstrator. It's a coaxial helicopter that's going along with the Perseverance rover on the Mars 2020 mission. And at the beginning of next year, it's going to perform the very first powered flight outside of Earth's atmosphere, and that's really exciting. So first, a little bit of background on me and how I got to be involved with this program. So on the very left, you see little 3-year-old Sara next to an F-104 starfighter, and you would think that there's a pretty clear path between little Sara and Sara now. But that's really not the case. I didn't know that this is what I wanted to go into until really late in high school when I was applying to colleges and trying to feel out what I wanted to do. And after I selected aerospace engineering, that opened up a lot of really great opportunities for me. And I was able to, as an undergraduate, I was able to be an undergraduate researcher working with microgravity flame combustion experiments on the space station. I was able to work on an autonomous vortex generator project. I was able to join a lot of clubs where I got a lot of hands-on experience building different things. I worked in the student machine shop, which is where I got a lot of my hands-on experience, learning how to build things, teaching other students how to build things. And all that experience led me to get an internship with AeroVironment between my junior and senior year. And that's what really led me to this career. And I came back after I graduated, and the first program that I was able to work on, and I'm really honored to have been a part of, is the Mars helicopter program. So why would we want a helicopter on Mars? Negin touched on this a little bit in her talk yesterday, but we have satellites that orbit Mars and take really big big area pictures, but they're not very detailed, and they're a lot like the satellites that orbit Earth that give you things like Google Maps. They take really high-level pictures. And then we also have rovers and landers on the surface of Mars, and they take really, really good pictures, but they're only from really close up, and you can't really see a large area. It takes the rovers a long time to travel from point A to point B and to go look at different things, so you really only get pictures of where you are. So a helicopter would be really useful to bridge that gap. And a helicopter can give you kind of an aerial perspective of what you're looking at, can go places that the rover can't go, like the edge of a cliff. It could go further and faster than a rover if there's something like over the next hill that you really want to look at. And so there are a lot of really great uses for a helicopter on Mars. And this program specifically is just a technology demonstrator. It's just to prove, can we fly on the surface of Mars? So back in 1997, NASA and JPL sent a mission called Pathfinder, which was a lander. And with that, they sent a little teeny shoebox-sized rover called Sojourner. And Sojourner's mission was just to drive around the lander and say, yes, we can drive around on Mars. And as a result of that, we've been able to send a lot of rovers ever since with their own science instruments, and that's been really useful to be able to explore a little bit more of the surface of Mars. And we're hoping that the helicopter can follow a similar path, and in the future we can do bigger and be more integrated with more and more missions as time goes on when this mission's successful. So how do you design a helicopter for Mars? So we started looking at our design as you would like an Earth-based helicopter, but everything's different on Mars. There's a whole list of unknown unknowns. There are so many things that we didn't know we needed to look at that we didn't know were going to be issues. There's no textbook and no handbook for how do you design a helicopter for Mars. It just doesn't exist. And we were doing a lot of things that no one's ever done before. And we had to approach them all in a really creative way. So what are some of those challenges? A big one is how far away Mars is from Earth. So when the helicopter is on Mars, there's a big time delay for communication. There's between 6 and 40 minutes between when you send a command, when you hear a command back. And as a result, the helicopter has to be completely autonomous. We can't just sit there with a joystick controlling it because we'll never know what we're controlling. So it's completely autonomous. Basically, we send a command that says go, the helicopter goes and performs its flight, and then we get the data back and we can say, yes, it was good. Another big challenge is the thin atmosphere on Mars. Mars does have an atmosphere, but it's only 1% the density of Earth's, and it's mostly carbon dioxide. And that was two big challenges for us. You only get 1% of the lift for the same geometry on Earth. And as a result, the whole helicopter has to be really, really light and has these really big blades that spin really, really fast. So on Earth, an Earth-based helicopter probably spins at 400 to 500 RPM, and this helicopter spins at 2400 RPM. So it goes very fast. And another thing that thin atmosphere does is you're not able to get rid of any heat into the atmosphere. There's no cooling from the air. And so as the motors heat up, as all our components heat up during a flight, we have to hold all that heat on board, and there's no way to shed it. And that's one of the things that limits our flight time. But on the contrary to that, at night, Mars gets really, really cold, and we have to prevent all our parts from freezing. So we have heaters on important components like the batteries, the computer boards, the motors, things like that, and it just keeps them from freezing overnight. And another thing is that it has to be completely self-sufficient. So we're not going with the helicopter. If it tips over, we can't just walk over and put it back upright again. The rover can't do it for us. One of the big things with this technology demonstrator is that we can't harm the rover. We can't put the rover in any danger because that's the main science mission for Mars 2020. So the rover is going to drop us off and then back away, and we don't come in contact with the rover ever again. We don't dock with the rover for charging or anything like that. So the helicopter has its own solar panel and batteries. and works completely by itself once it's dropped off. So the one of the other big challenges is being accommodated on the rover. So we're a hitchhiker. We're hiding out under the belly of the rover, and you can see us kind of folded up and tucked in that red circle. And that really limited how big everything could be. That limited the size of most of our components, and that was fitting into that tight envelope was a really big challenge. Another big challenge was all our components had to be fabricated and assembled in a clean room facility because it had to be so free of contaminants. Mars 2020 is looking for signs of biological life, and it would really suck if we send all this to Mars and Mars 2020 says, hey, we found life, and we look into it further and we go, oh, those are Sarah's fingerprints all over the helicopter. So we had to assemble everything in a clean room facility and keep everything totally pristine for this mission. Another big challenge is the launch vibrations. Most helicopters don't sit on the tippy top of a rocket and go on this controlled explosion to space. And so instead of just our operational flight loads, most of our components were designed to handle these really intense launch vibrations. And so what does a Mars helicopter look like? What is it made up of? So this is what we call our rotor system. So there's a central carbon fiber tube, which is the main backbone of the whole helicopter. And that's just like a hollow tube that's really strong. And then on top of that, we add two almost identical rotors that contain a hub in the very middle, and that's what contains the bearings and helps everything spin. A propulsion motor that drives that hub. And then we do two rotor blades on each of those sides. And then below that is a servo and swash plate mechanism, and that's how we control the blades. So we take that whole rotor system and we add onto that, we add a solar panel up top and an antenna. And then down below we have the landing gear, and we have this shroud. It's like a film shroud that makes up the helicopter warm electronics box, the HWEB. And inside of that are the core electronics. That's the batteries, all of our computer boards and things like that. So the HWEB is both a thermal barrier, it keeps things warm at night, and it's a dust barrier to keep all those boards and cameras clean. And then, so let's see, some of the main components. This is the propulsion motor. We talked about how everything had to be really small and was constrained by how much room we had under the rover. So this is a very thin, very small, but very high efficiency, very high power output motor. And it's pretty impressive because it's only 2 inches in diameter, but it directly drives this 47-inch diameter propeller, and there's no gearing, no nothing. So it's really, really impressive. And then we talked about how we can control the blades, and we do that through a swash plate and servo mechanism. So how that works is each rotor gets one set of these, and those 3 servos are a little motor with a little arm on it. And when we move that arm, the swash plate, which is that like donut shaped mechanism, will tilt around. And when we tilt that mechanism transfers that displacement from the stationary frame of the servos to the rotating frame of the blades. So as the blades go around, they then tilt by however much the swash plate was tilting, and that's what helps us control up, down, left, right, forward, back, things like that. And the landing gear was a really interesting problem. We really need landing gear because that's what protects the helicopter when it lands. So we have this titanium spring, which is like the bottom half of that curved piece you see. And that spring is what keeps, like when it lands, the legs kind of splay out, and that's what keeps the H-web from just like smacking down on the ground. But as it's a spring, it's really springy, and the helicopter could bounce around almost forever. And so we really need to absorb all that energy, and you can't use a lot of the things we would normally do to absorb energy, like friction or like an oil damper or anything like that, because they don't work the same way on Mars. We don't understand well enough how friction behaves on Mars, especially dependent on humidity and surface conditions and temperature and things like that. So we couldn't use any of our traditional methods. And what we came up with is actually really clever. It's a piece of thin, really, really soft aluminum. And as the leg flexes, the aluminum deforms. And that deformation is what absorbs the energy of landing. And it flexes back and forth and yields a little bit. And that's what helps absorb all that energy. And then at the very top of the leg, you can see a little carbon fiber yoke. And inside of that is a whole series of latches and springs. And that's what allows the legs to fold up and be stowed for travel, and then deploy and lock for when we're ready to fly. So again, we talked about that really tight envelope that we have to live in. So in the top, you kind of see that helicopter laying on its side, and that's how it's stowed under the rover. And you can see all the legs, they fold up near the blades, and then they deploy as we release the helicopter. So you should be able to see that little video moving, and the helicopter rotates kind of from horizontal to vertical, and those back legs deploy automatically as that happens, and then the front two legs are deployed as like a secondary operation. And when we're working with the rover team, they kind of tell us, here's where your leg is allowed to be, here's where it's not allowed to be. And as a result, all four legs have this unique angle that they fold at, and it's extremely asymmetric. So you can see that one leg is held kind of at its ankle, and then when it rotates down, it pokes up into the belly pan, into that little pocket. But on the other side, there's something really important on the other side of the belly pan, and we weren't allowed to put a pocket there. And so that leg is held just a little bit lower, and that leg is held like on a special little loop on its foot. And so that's why one foot is different than all the other feet. And then every component on the helicopter had to be super, super, super optimized to get the lightest system possible. We talked about how important it is that the helicopter is really, really light. And these two parts are really great examples of that. So one question we always get is, what are those horns, or what are those spikes, or what are those things that are sitting on the blades? And those are hollow carbon fiber cones, and they have a little ton of weight in the tip. And the reason for this is, as the blades spin, they load the servos based on what we call the tennis racket effect. You can kind of imagine this if you hold like a tennis racket in your hand, but hold it kind of loose so that it's a little bit free to rotate, and hold it up and down, but spin around really fast, it'll tend to try to flatten itself out. And our blades do the same thing. And normally you wouldn't have to worry about this, but since our blades spin so much faster than on Earth, this effect is really, really strong. And because of that loading on the servos would either need to be a lot stronger and therefore a lot heavier, or we apply this counterweight, and that reduces the servo loads, and the total weight of the system is less. And that's why that made a lot of sense to do that. And then another component that's super highly optimized is that mast, the center tube that runs up and down the whole backbone of the helicopter. So inside the mast are all the wires for all the components. They go from the batteries in the bottom. They go from the batteries in the bottom by that fuselage, and they run up through the mast, and they poke out little holes along the way to get to the motors, to get to the servos, to get to the solar panel up top. And so the mast has all these little holes drilled in it for access for those wires. But that makes the mast really weak for those really strong launch vibrations. And so we needed to make the mast a lot stronger. But in order to make something stronger, you have to make it heavier. And the way we got around making it too heavy is we added these little carbon fiber flutes up and down the whole length, and that's what gives it that kind of flower pattern in the center. And so that extra carbon runs just around each hole and locally transfers that load around each hole and makes it just strong enough without making it too heavy. So how do we make all those parts? So all those parts were fabricated and assembled in clean rooms. And on the left, you can see that's me, and I'm assembling the landing gear plate, which is kind of this X-shaped plate that sits on the bottom. And you can kind of picture how each leg would come off of one of those legs. And in that picture in the middle, we're installing landing gear onto one of the test vehicles. And then on the right, that's a really good bare bones picture of what the helicopter looks like when it doesn't have its blades installed, doesn't have the legs installed. This is what it kind of looks like without all that stuff on top. So once we fabricate the whole helicopter, we send it over to JPL, and they start running tests on it, and they start integrating their components, and we kind of work up from there. So they do kind of a low speed spin up test, and they do some system identification tests. One of the really cool things is that we got to pass through all of these kind of historic facilities at JPL, and it was really neat to see our hardware pass through those facilities. For example, on the far right on the top, you can see kind of like a silver tarp, and under that is one of the science instruments that's on the space station right now. And so it was really neat to see our hardware kind of pass through all these gates and pass through all these clean rooms and all these historic programs. Like every Mars rover has been through these clean rooms. So it was really cool to see that. So after we're kind of integrated into JPL, we go through a whole host of environmental testing, and that's to make sure that we can survive the trip to Mars and also survive surface operations on Mars. So we run a thermal and vacuum test, and that happens in that big chamber on the bottom right. And you can kind of see a little helicopter that he's working on there. And that big door slides to the right and closes, and they pull it down to vacuum, and then they get it really, really cold, like Mars, and they test things like, can we survive overnight? Do all our mechanisms work when they're really cold? Do our little heaters work so that we can start up if it's cold? And then we go through shock testing. So there's a big shock event that happens directly to us. There's a lot that happen in the deployment of the rover, but there are a couple that happen directly to the helicopter. Most importantly is the one that finally drops us off on the surface of Mars. So they basically break a bolt that's holding us at the very tippy top, and they just break that bolt and we fall to the ground. And so they had to test that. They did that for real, and they tested that both at room temperature and cold. We tested that in the cold chamber as well. And then we also have to test launch vibrations. And on the right in the top, that's a big shaker table. And you can see the little helicopter in the corner, and they'll put it on that fixture on the table and then just shake it to death and make sure that it can survive the shaking of being on top of a rocket. And then of course we have to do flight testing, which is really hard to do on Earth. And we did that in JPL's 25-foot space simulator, which is a 25-foot diameter, 80-foot tall, basically a pressure vessel that's just a big vacuum chamber. And what they do is they can pump out all the air to almost hard vacuum, and then they backfill with just a little bit of CO2, and that mimics the Mars atmosphere. But we can't really mimic Mars gravity. So Mars has 3/8 the gravity of Earth, which helps a little bit, but it's not enough to offset how much lift you're losing from the atmosphere. So we have to apply this gravity offload tether, which is like a little string that we attach to the very top of the helicopter, and we hook it up to a motor at constant torque, and it just pulls up on the helicopter just enough so that it thinks it's in Mars gravity instead of Earth gravity. So this is a video of one of the test vehicles in that chamber doing a flight test. And it's stabilizing itself using those markings on the ground, all those little tape X's. And it'll do the same thing on Mars, but we won't have tape X's. It'll use features on the ground like rocks and little cracks in the ground and things like that. And it'll use that to stabilize itself, and it does that all autonomously. And it's pretty impressive how smooth the control is on this helicopter. It's almost uneventful to watch this video because it looks so nice, but a lot of hard work went into making that happen. So then what happens after we're all tested, we're all ready to go? What happens next? We get integrated onto the Perseverance rover for even more testing, and we go through basically all those same tests again with the rover. And you can't really tell, but under the rover, there's a little teeny shadow that is the helicopter. And then after we go through all this testing with Perseverance, they pack us up in these big crates and fly from California out to Kennedy Space Center in Florida and get ready to get packed up for real. So this is the helicopter getting installed onto the belly pan for real. And what they do is they take the belly pan bottom side up and they install the helicopter, and then they flip the rover over and use a crane to lift that belly pan onto the rover and secure it. And then they flip the whole rover back over, helicopter and all. And then they take, just for, pay attention to the scale here, there's this little helicopter on the left, you can see it on the belly pan, and then we're with the whole rover now, and the rover is now installed in this back shell, which is this big enclosure that it rides into space. And it'll ride in this spacecraft to Mars. And then they install a little black dust cover on top of the helicopter to protect us from dust and debris when we enter the Martian atmosphere, and then also when we're riding around under the rover before they drop us off. And then they install this heat shield on the bottom. And that's to protect the whole assembly as it enters the Martian atmosphere. And then that whole assembly, that whole picture we just looked at, is just this little spacecraft at the bottom of this rocket fairing. And what's missing from this picture is the Centaur second stage, which is like a second rocket motor that lives where all the blue padding is. And then this spacecraft will sit all the way up in the tippy top where the black is. And then they close that whole thing up, and they use a crane to lift it all the way on top of this huge rocket. And then in July of this year, on July 30th, we launched and left Earth to never return. So you can imagine this teeny little helicopter in the very, very tip of the rocket, just on its way to Mars. So that's what we're doing right now. We are cruising on our way to Mars. Everything looks good so far that we know of. And then on February 18th of 2021, the whole rover will descend to the surface of Mars, and we'll start what's called commissioning of the rover. They'll wake it up, they'll check and make sure everything looks good, make sure we can talk to it, and then it will drive around for a little bit, and it will find a nice flat spot to drop us off in. And we will we'll then start our own commissioning, make sure we can talk to the rover, make sure the rover can talk to us, make sure all our stuff looks good, and then we'll start a 30 Martian day mission, and we're going to attempt to do 5 demonstration flights, the first of which will kind of be just kind of hop up and hover and come down. And then when that looks good, we'll go up and over a little bit and back down and build from there. And those will be the very first powered flights on another planet, and that's extremely exciting. That's a big thing that humanity's never done before, and hopefully that'll start opening a lot of doors for space exploration that we haven't done yet. So with that, I think you are pretty well introduced to Ingenuity, and I think we can do some question and answer.
Totally. Sarah, this is so cool. I have so many questions myself, so let's start out with some questions that we have from our participants. For everyone tuning in with us, right, we're here with Sara Langberg, who just gave us this awesome presentation on the Ingenuity helicopter that's accompanying the Mars 2020 Perseverance rover. And will be the first time that we have this kind of technology on another planet. So friends, ask all of your questions in the chat window. Feel free to type away your questions. Again, we want to give priority to folks who, some of our younger participants, who are also looking to have a career in space exploration, and maybe some of these questions can help them get there. So Sarah, the first questions we're going to start out with have to do with this idea that it's a demonstration of tech. So you mentioned that this is going to be about a 1 month long series or experiment time where there'll be 5 different missions. Do you expect it to last longer? Like, what is the life expectancy of Ingenuity? And do you anticipate to get more than just those 30 days of mission time?
So we would be absolutely thrilled to get through our 5 flights in 30 days. Because we're a tech demonstrator, we're not the most important mission in Mars 2020 in the whole mission. The rover has really important life-discovering science to go do. So after 30 days, the rover has to go off and do its own science missions, and we'll lose communication with the helicopter when that happens.
Wow. So this is a short but sweet mission then, if I'm understanding correctly.
So it'll be short, but we'll be able to. The helicopter doesn't really have any payloads of its own, so we'll get some really cool pictures of it, and some really good flight data back from it. But beyond that, there's not a whole lot it can really go do.
Right.
So we're basically proving out feasibility and saying, yes, this is a thing we can do, and we're going to use that data to open up future missions.
So on that note, when we're talking about, trying to develop this kind of emerging technology that we hope to see in future planetary missions, how long does it take? Like, we saw that you told us how you went and did some testing at JPL. How long did that site testing take place at JPL? And how long was the process from the first ideas of this helicopter to launching it in July? How long did that take? Months? Years?
So I've personally been on this project since 2016. But the idea of having a helicopter fly on Mars is from like way back in the 90s. And we've had this idea and we've been working on this idea, but there hasn't been a good opportunity for us to really be a part of this mission. And that's what's really exciting about 2020 is that we finally got funding and we finally got the opportunity to go with the Perseverance rover to try this for the first time. And so we are at AeroVironment, we started working on this project probably in 2014, I think, with those first conceptual projects. And then each helicopter probably takes a couple months to build and months of testing beyond that.
A long time.
A long time.
A lot of work goes into creating these this really incredible technology.
One of the interesting things is that this is a really short program in terms of space exploration. Kind of the idea of doing a tech demo is that it allows us to do these things cheaper and faster than a whole flagship mission, which is really special for what we're doing.
So how is that going to work once you do get into this period where we successfully land, we have 30 days to do some testing? You mentioned that's completely autonomous. So are there people who are managing the operations back on Earth and just code in a program and then send it? Is the data and pictures coming back through Perseverance, or does the Ingenuity beam it back directly to Earth? Can you just tell us a little bit about operations once it's doing its mission?
Yeah, so there's a whole team of people at JPL who are working on operations. They're working right now, planning what we're going to do, planning how that whole process is going to work. And yeah, we pretty much take code that we have tested here in the chamber and upload it to Ingenuity and press go. And Ingenuity can't talk directly to us, but Ingenuity will talk to the rover, who will send that data back for us, either directly or through an orbiter around Mars, depending on where Earth and Mars are relative to each other.
Awesome. And you've talked about how you had to accommodate the very harsh environment of Mars in order to protect your rover and make it functional. So we have someone who asked a question about this. Are you concerned with radiation damage to any parts of your helicopter in transit to Mars?
Yeah, so that's part of the reason why the rover and the helicopter underneath it are housed in that big spacecraft, and that holds a lot of special things for us. It has solar panels to help us get power through that whole cruise stage for those many months. It also has ways for us to send out heat and protection from radiation and from the cold of space as we're traveling.
Awesome. Okay, I have a few more questions about Mars. So, you did so much work in your own career to understand aeromechanics, aerodynamics on Earth. What did you have to do to prepare to create something that would have to work on Mars?
Well, so the math and the science pretty much still hold up, even at a lower density. So that part, I don't want to say it's straightforward, but it still holds true, and we're able to use that as a really good design tool. But there are a lot of things we don't understand. There were a lot of flight dynamics issues early on that we had to overcome, and that was with a lot of analysis and testing. And it's very impressive how well controlled the helicopter is now, based on where it started early in the program.
I can imagine. Okay, a couple more questions about Mars. Mars has crazy weather. How are you going to deal with the wind and dust storms when flying the helicopter?
So the helicopter can survive some winds. One of the interesting things about the low density of Mars is even when there are these big dust storms that come through, the low density means they don't feel the same intensity like you would on a windy day here. So they're not quite as intense as you kind of are imagining. But the honest answer is, if there is a huge dust storm and for some reason we tip over or get covered in dust or something, there's nothing we can do about it. We're here on Earth and it's on Mars, and we don't have a good way to fix that. But because we have such a short mission window, we can kind of cater to that and get our missions in when the weather's good.
Awesome. I really hope you have good weather for the entire time that you were doing your mission. So this was actually one of our early questions I have for you next, and this is one that we're continuing to see. With this helicopter, with Ingenuity, it's a demonstration of tech, and that's really exciting for the promises it potentially holds for future planetary explorations. So what do you feel is the new technology or discoveries that we can expect in the coming eras of space exploration? This is from a teenager who just mentioned, as an aspiring physicist, this is so cool. I agree. This is so cool. What kind of tech?
The possibilities are limitless. I mean, even just for this helicopter could go on to assist future rovers, go assist a lander. We could send a whole fleet of these helicopters to go look at other things. Maybe eventually send it with an astronaut, and they can explore Mars together. So even just for this helicopter, like, there are so many possibilities of ways we could use it. And technology is coming up so fast right now that it's evolving faster than we can even have ideas of what to do with it.
Do you think that we are going to be seeing a lot more helicopters in the future?
I hope so. That would be really cool.
So if we could switch topics a little bit, we've been talking about some of these nitty-gritty details about how do we actually do a Mars-related mission. But Sarah, something that's so cool is that not only do we get to learn about this awesome technology, but you got to build it. You mentioned at some point, when you're in the clean room, like, you can see me working here, and if it wasn't for your glasses, I wouldn't know, right? You get to have such an exciting role in this kind of developing technology in order to push forth our understanding of outer space. And so we have a lot of people who are logging on who want to know how they can become you, how they can also work in the aerospace industry. So the first question on that is just, what kind of recommendations would you give to someone who's maybe a teenager who's looking to get involved in the aerospace industry? What words of advice would you pass along?
The biggest advice I could give you is be outgoing and try new things, even if you don't think you'll be good at it, even if it's hard. Just be willing to get in there and get your hands dirty, get hands-on experience, build things, sort of invest in hobbies that help you learn how to do that. Oh, my lights are turned off. And really just be willing to put yourself out there and pursue what you're passionate in. There's no like textbook for this is how you become an aerospace engineer. This is how you work at NASA. Go for what you're passionate about. NASA needs geologists and scientists and even just people who are good communicators. And pursue what interests you more importantly than say, here's what I want to do. And if you follow that, you'll kind of end up where you want to be.
That's awesome. I think that's a really important thing to remember, is there's no one way to succeed, right? There's a lot of ways that you can get involved in this industry. And as you mentioned, you can do it from an engineering perspective or in a variety of other ways to help participate in, pushing forth humanity's understanding of where we are in space. Okay, so I'm getting a few more questions. We have a lot coming in, so I'm just looking at them. Friends, if you still have questions, this is the time. Keep on sending them along. Okay, so let's see. We have a couple questions about your organization, because you mentioned that you originally interned there, and then you came back to work there. So when you first started interning there, were you working on Mars-related missions? Is that all your organization does? Does your organization hire all kinds of people? Is it only engineers? Will they hire PhDs? Do they hire interns? What is it like to work at a place that develops this kind of technology?
So what's really interesting is that AeroVironment, this is our only space mission. This is the only one we've ever done like this. We do a lot of other work. We do a lot of work for the military. We do a lot of work doing other unmanned aerial systems. And so that's kind of what I was working on when I was an intern. I was doing a lot of, it was a lot of hands-on work, a lot of learning to build things, a lot of work with composites, a lot of work with like some design tasks. And when I came on full time, that was my first introduction to the Mars helicopter program. And we work with all kinds of people, engineers, all levels, interns. We need computer science people. We need legal people. We need everyone. We need managers. It takes a huge village to make anything like this really happen.
Absolutely, it takes a village. Do you see yourself continuing to work on this? Are you on this project through the end, or what are you doing right now until February when it lands?
So I'm actually working on a lot of different projects right now for a lot of different things. I haven't been actively on the Mars helicopter program since we kind of handed it off to JPL after we built it. So I'm just kind of following its journey with everybody else at the moment.
I think it's going to be very exciting when it lands. I remember watching the landing of Curiosity and how nerve-wracking it was, even as someone who was not at all involved. So in some ways, I'm glad you guys get a little break from the launch window before it actually reaches Mars. Gives you some time to regain some composure.
Yes.
Okay, so I'm actually getting some questions on the kind of other technology you've worked on. For the other projects you've worked on, have they been other helicopters? Have you worked on satellites? What are some of the other things you've been able to build in your career?
So outside of this, I mostly do like a fixed wing airplane kind of stuff. I do a little bit of everything. I do a lot of math. I do a lot of design work, but I also, one thing I love to do is build things. And so I'm really grateful that here at AeroVironment, I get to do both. I do a lot of composite parts. I do a lot of tooling for those. But one of the really cool things working on kind of this prototype level work that I do is that I get to design the part, design the tool, and then I just get to go build it and test it and see how it works. And if it doesn't work, I get to go back to the drawing board and fix things. And I really enjoy being able to be through that whole process and do things instead of like a big production program where you design one little bracket and then you hand it off to the other guy who does a little bit more analysis, and you hand it off to the other guy who builds it. And so one of the really unique things that I get to do here is I get to be a part of that whole process. And I really like being able to do both the design and the build phases of all my programs.
That's so cool. And I think that's something like that you bring up that I think is different among different professional organizations, right? Maybe there's some people who are engineers who are just going to do the CAD drawing or going to do the tech specs and then pass it off. But it's really cool that you get to be involved with the production and the testing capabilities as well. As someone who also loves making, do you have a favorite aspect of the design process or a favorite making tool you use? Is there a CNC machine you just love? Is there one aspect where you just get really excited about the design process?
That's tough because I really enjoy the whole process. I think my favorite part is seeing things become a reality. You know, I design them in CAD, I see them on the screen, I spin them around, and then you order your parts and you start making things. And that process of going from the purely conceptual to parts that I'm holding in my hand, I think is really cool.
That is awesome. We have a couple folks who are asking to want to know more, and I'm assuming that they can probably Google AeroVironment if they want to learn more details about your organization that you work for.
Absolutely.
Awesome. Okay, so we're getting a few more questions here. In order to make sure that everything would work with regards to the Ingenuity helicopter, how much did you rely on computer programming simulations versus maybe like a quote unquote live simulation? How much did you rely on computer simulations to help nail out all your errors?
So for different aspects of the program, we kind of approach them very differently. So a lot of the parts, because it was a quick and kind of on the cheaper side of space exploration program, a lot of like our composite parts, the landing gear plate, the mast tube, things like that, we did kind of a medium amount of analysis of computer simulations. And a lot of what we would do is we would build one and then test it and see where it breaks, and then make it a little stronger and then see where that one breaks. And we would pair that with our analysis, and that's how we get a really good analytical model. But then there were a lot of things that you just can't test. So a lot of the controls, a lot of the computer algorithms that actually make the helicopter fly, that is heavily reliant on computer simulations. And we were able to really dial that in before we ever got into the chamber to do that testing. So it really depends on which part of the helicopter you're thinking about. They all use a little bit of computer simulation and they all use a little bit of testing, and how much of each is really dependent on what it is. Landing gear is another really good example of that. We don't have a good model for what landing dynamics look like. And the best way we could see if our landing gear was going to hold up was we built this big concrete platform, and then we put sand on it and we put different surfaces on it, and we just took this little test model and we would drop it on this little concrete platform, and we would drop it in the sand, and we would like push it over and then drop it to get some kind of side velocities going. And that was the best way to test landing gear, as opposed to build up a huge simulation model.
Wow. That's really interesting to think about the challenges you have with testing and trying to create this kind of Mars-like surface in order to keep dropping the rover, dropping the helicopter on it. So this actually is another question about testing. So, you know, for other Mars-based missions, you know, I believe that they have an exact replica of the Curiosity here on Earth that they can continue doing testing and engineering tests. Do you guys have other replicas of your helicopter that you can do the same? Do you just have that one that you sent off, never to return again?
So the only one that looks exactly like the one that went to Mars is the one that went to Mars. We have two very similar test vehicles that we can work with here on Earth. We have one that did flight testing in the chamber, and so if we need to like practice a flight test for Mars, we could practice with that one in the chamber. And then we have a second one that went through all of the thermal and shock and vibration testing. And so they have very small differences from the final vehicle, but they're all close enough that we could perform tests on those to get a good idea of what would be happening on Mars.
Awesome. Okay. Couple more questions about designing this. First off, how much does it cost? How much does it cost to send a helicopter to Mars? Or how much does a helicopter cost to make?
A lot. One of the reasons that a helicopter hasn't been sent before is it costs a lot of money to send something to space. There's a lot of cost in just the engineers who design it. There's a lot of cost in building the parts. you need a lot of specialty parts. We needed a lot of things that you can't really get anywhere or make anywhere. And one of the things that allowed us to actually go to Mars this time was NASA actually put us as a line item in their annual budget. And so we weren't even guaranteed to get on the rover until I think May of 2018, when they finally made the decision, yes, you're allowed to come with us.
That's a lot of work before you get that go ahead.
Yes.
Okay. So we have folks who, for those of you who are with us, we have another 10 more minutes maybe with Sarah. Keep coming, keep sending in your questions. We have one about the nature of the mission it's going to do. So you said there's going to be maybe 5 different activities that the Ingenuity helicopter is going to attempt over the course of a month or so. Can you tell us about what some of those activities look like? And we have some questions about the details. How high is a helicopter going to fly off the surface of Mars?
So I think I'm not positive on all these numbers because I haven't looked at them in a while, if I'm being honest. But I think it flies up to about 10 meters, about 30 feet.
It's not very far off the surface. That's what we're talking about. This is going to be a low flying craft.
So the whole point of the mission is just to prove, can we fly on Mars? Yes, we can fly on Mars. So we're not trying to do anything crazy. The first flights are really just going to be take off, hover, and come back down. Take off, hover, go over here, come back, and back down. If we're getting really crazy and doing really well, we might, if we see another good landing site, like kind of come up and go over and land right next to it. So we're really just kind of testing these waters and feeling out how feasible are these things on Mars. It's not going to do anything totally crazy. It's not going to go perform aerobatics on Mars or anything like that.
I don't think you're giving yourself enough credit when you use the words totally crazy, as this is going to be the first of its kind.
Sure.
It's really exciting.
Yes.
So with regard to this, you got to see this process, since 2016. I think you mentioned over the last 5 years. Do you have a favorite part on the helicopter that you designed, or maybe one that you find particularly innovative that you like to highlight? You showed us a few of those, but what's your favorite?
I think my favorite thing that I got to personally do is that landing gear plate, and that was really challenging because of it being so asymmetric for a lot of different reasons, and that was one of the parts that I really got to see from beginning to end. So I designed that part, I designed the mold for it, and then I physically made the parts that are going to Mars, and that's, like, I cannot describe how exciting that feels.
It is so cool. Now, for those of us who are going to be watching at home who didn't actually get to build a part that goes to Mars, if your mission is successful, will we get to see some of the photos? Will we see one of the photos with the shadow of Ingenuity in it, looking down at the surface?
Quite possibly, yeah. So the helicopter has 2 cameras on board. It uses one for navigation and one to send color photos back, and it's a lot like the camera in your cell phone. So it's going to go take like the universe's coolest selfie. We're going to go take a picture of the rover, and the rover's going to look back and take a picture of us, and it's going to be super cool. And hopefully we'll get some of those pictures back, and we'll get to see that.
That is so cool. So you mentioned they'll take photos of themselves. How far apart can Ingenuity and the rover be? Can they be pretty far apart? You mentioned that once it goes too far away, that's probably going to be the end of Ingenuity. But do they have to be buddy-buddy right next to one another? Can they be a little bit far apart?
Yeah, in fact, we don't want them to be buddy-buddy next to each other. We talked about being safe to the rover and how we can't interfere with the rover's main science mission. So if something goes totally crazy and we go crashing off sideways, we need to make sure the rover is far enough away that we don't harm the rover at all. So the rover, once they drop us off on the surface, it'll back up, it'll help us do an inspection, take some pictures, things like that, and then it'll back up to a pretty far distance, probably about a football field's distance away, and then let us go from there. And that's mostly for safety to the rover.
Wow, really interesting. Okay, so we have time for just a couple more questions. This one has to do a little bit with this timeline that you had. So potentially this it's like mid-February, end of February is when when both the rover and the helicopter potentially get to land on the Martian surface. If everything goes according to your scheduled timeline, when would you expect to be carrying out this 30-day mission?
So I think it's about 30 days of commissioning just for the rover itself, and then they go around and find a good place to drop us off, and then they have to drop us off, and then we start doing our own commissioning. And so I think that's about 30 to 60 days. So we're looking at like an April, May kind of timeline.
Awesome. And this, of course, happened during the pandemic. How has the COVID pandemic changed your work?
So the pandemic has really been hard, especially on the engineering team at JPL. Being offsite, everyone's remote. Only the people who like really need to be there get to be on site. So they were really protective, for example, of the team that's actually doing the final installation in Florida, because that was happening right around March, April timeline. So they were really quarantined, and they were really protective of that team. But most of our stuff had already been handed off previous to that. So it was really just kind of, it was shipping to Florida, and that final installation that was really tricky, having half the team offsite and only having the people on site that really needed to be there to do physical installations and things like that.
Right. And for those of us, someone was asking, where are you based right now?
We're in Simi Valley, California, which is just like a little bit north of Los Angeles.
Very cool. Okay, our final question for you, and I feel like you touched on this a little bit, but I'm just going to read it directly, quote unquote. Sara, you are so cool. What is your favorite individual accomplishment on this project?
I think the thing I'm most excited about is that parts that I made with like these two hands are going to go touch the surface of Mars. And I like can't even quite wrap my head around that, which is insanely cool. And then one of the other really exciting things I got to do was go to Florida and see the rocket launch from Cape Canaveral, Florida. And that was such a cool moment. Again, it's really hard to wrap your head around. Things that I made are no longer on this planet. It's just totally mind-blowing.
For us as well, Sara, thank you so much for taking the time to talk about all the exciting work you've done. I can say for myself and pretty much everyone else on this who's participating in this call that we're really excited for you. We can't wait to see what happens to the Ingenuity and future helicopters in these planetary missions. Thank you so much, Sara.
Thanks for having me.
And friends who are joining us, the fun doesn't stop here. Join us tomorrow. We'll have a wonderful presentation by Monsi Roman. She is so cool. She went from an island girl in Puerto Rico studying marine microbes to a chief microbiologist at NASA. So learn about her journey working with these life support systems for space that are even featured on the International Space Station. Again, a very big thank you for Pisces for organizing this really wonderful Women in Space Exploration talk series. Thank you so much, Sara Langberg, for coming and talking to us about the Ingenuity helicopter. And you know, we want to make these programs really exciting for you. We want them to be fun and stimulating and beneficial and interesting. So please, 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 if you have some time, check out our feedback survey. You can use the QR code on your screen. There's also a URL link that'll also take you to the survey as well. And of course, a very big thank you to our sponsors, Microsoft and the Hawaii Science and Technology Museum. Again, my name is Mimi Fuchs. It's been wonderful being with you here today. And hopefully I see you tomorrow for our presentation with Monsi. Mahalo, guys.